Oh, hi. Didn't see that there. Whoopsies. Anyway, this is Mr. Cox giving you another video. This is the second part to our Earth as a system unit. So let's take a look, right? So we've talked about this law of thermodynamics, right? Energy can neither be created nor destroyed. It can only be transferred from one form to another. So for instance, right, the light coming out of this light bulb, if I shut the electricity off, then the light stops working. So electrical energy is traveling up the wire into the light bulb. The light bulb is then being excited. The particles inside that light bulb are being excited by the electrical energy, and when the particles excite, they give off light. So that's transferring from electrical energy to light energy, right? The world does that all over the place. So conservation of energy, it cannot be created nor destroyed, just transferred from one form to the other. Same thing with matter. Matter can neither be created nor destroyed, just transferred from one form to the other, okay? As a review, right, talking about what matter and energy are. Matter, anything that has mass and takes up space, right? So everything around you has mass and takes up space. It's made of matter. You're made of matter. That desk is made of matter. The cup is made of matter. The water is made of matter. Energy is just the ability to do work. So it's the ability of something to do work. All right? That's all. Energy does not weigh anything. It has no mass. It's just the object's ability to do something. If we look at Earth as a system, right? An organized group of related things that work together to make a whole, right? To work together to do something. Earth as an entire system is more made up of four smaller systems, right? The hydrosphere, the atmosphere, the biosphere, and the geosphere, okay? Now, these four systems independently, so if I just look at the hydrosphere is an open system. Matter and energy can flow in and flow out, okay? If I look at the biosphere, matter and energy, so when a child is born, matter just added to the biosphere. When a person dies or an organism dies or a plant dies, that matter is then broken down and released into another sphere. Maybe the biosphere, maybe the hydrosphere, some to the atmosphere. But the biosphere lost matter and the other spheres gained the matter. Okay? Along with energy. But an open system, matter and energy can flow in and flow out easily. Okay? Now, if we look at all four systems together as one big whole, right? One large unit called Earth. Earth is a closed system because matter does not change on the planet. The matter that's been here is the same matter that's been here for 4.6 billion years, for the most part. Okay? So, that's what this is talking about. Okay? The four systems are open systems, meaning matter and energy can flow in and out of the system freely. But Earth as a whole is closed because the only thing that can flow in and flow out is energy. Matter does not. We do not lose matter and we do not gain matter on a grand scale. Now, we talked last notes about meteor showers adding some matter and man-made objects, right? Satellites being put out to space and hydrogen and helium atoms being lost to gravitational pull. That's so insignificant that we truly define Earth as a whole as a closed system because the amount of matter gained and lost is really negligible in comparison to the amount of matter that Earth is made of. So, Earth is a closed system. Got it? Okay. Let's stay on the idea of energy, okay? So remember, energy is not matter. Doesn't have mass, okay? It doesn't take up space. It's just an object's ability to do work. So, there are two sources. If we just look at Earth, there are two sources of energy for Earth, okay? There's an internal source of energy, and then there's an external source of energy. Let's take a look at the internal source of energy. Deep within our Earth, there's a heat source from two different processes. So, internal source of energy inside of Earth. Now, there are two processes that give us the heat or the energy that we need. Okay? The first one is called radioactive decay. I know you learned about that before. Radioactive decay, right, is radioactive material that breaks down over time. There's what's called a half-life. right? And as that material breaks down, it gives off a massive amount of energy. Okay, so atoms in Earth's core decay slowly, and when they decay, they release energy as heat. So as those products break down, they release energy as heat. That energy radiates out towards the surface, and we feel some of that heat. Okay, that's the first thing. So radioactive decay. The second thing is gravitational contraction. Gravity pushing things towards the center of Earth, right? Particles are constantly being pulled towards the center of Earth, where they're heated. As they're heated, they're pushed back out towards the surface, causing a cycle called convection currents. And this causes friction, which causes heat, right? So gravity's pulling them in towards the center. As they move towards the center, they get heated up and they want to get pushed back out towards the surface. As they move out towards the surface, they lose their heat energy and they get pushed back down towards the core. And as they get pushed back down towards the core, they heat up and move back towards the surface. And it's this perpetual cycle called a convection cycle that keeps the flow of the mantle moving. That's what causes the flow of the mantle to these convection currents, where very hot magma is being pushed out towards the surface of Earth and cooler magma is being pushed towards the center. So that perpetual cycle causes friction between all of those particles, and that friction causes heat. Okay, so that's the internal source of energy. That's within Earth. What do you think the external source of energy might be? You're right. All right, external source of energy. Energy that the Earth is affected by two external sources of energy. The main thing, right? The main source of external energy is the sun. Solar radiation warms Earth's atmosphere and surface. Okay, this causes air masses to heat up, which generates wind and ocean currents. So the sun causes different parts of the globe, different parts of Earth to heat at different rates. And that causes a difference in air pressures. And difference in air pressures causes wind, right? Because everything on Earth wants to be balanced, right? Okay? So the sun is the main external source of energy. Now, we also have what's called the Moon-Earth-Sun gravitational attraction interaction that causes an external source of energy as well. Okay, we don't necessarily think about this, but it really does. So the moon and the sun and the earth in their configuration around each other causes tide. And I know in 7th grade you learned about tides, so we're not going to spend a ton of time on that, but the moon, the earth, and the sun, as they line up in different positions, their tides are created. All right? So the interaction between the earth, sun, and the moon, gravities collectively generate tides. Well, how does that do anything? So those tides bring massive amounts of water in towards shore and then massive amount of water away from shore. And that constant movement causes ocean currents and causes the mixing and the churning of the ocean. It helps the churning of the ocean. So if the moon flew away, our oceans would slow their mixing and their churning. It may not stop, but it would severely slow it. So that's an external source of energy. The moon, the sun, and the earth, all configured around each other, causes these bulges of water in certain parts of the world. So that's an external source of energy. Okay? Now, let's take a look at Earth's surface. Earth's surface is warmed by 3 different processes: radiation, convection, and conduction. All right, let's take a look at radiation. Radiation is the way that sun energy gets from the sun to Earth's surface. Radiation needs no particles whatsoever to get to where it needs to go, right? It travels from the sun to Earth through waves, and waves do not have to travel through particles in order to get to where they need to go. They can travel through empty space, all right? So that's how the energy gets from the sun to Earth. It only takes, it's the only energy that travels through empty spaces. Conduction and convection cannot travel through empty spaces. They need particles to transfer their energy. All right? Solar energy enters the atmosphere, starts warming the atmosphere, hits the surface of Earth, and begins to warm it up. All right? So we've got a couple different images. Right? So Earth's incoming solar radiation, right, enters our atmosphere, hits the Earth. Some of that energy is absorbed, right? Absorbed by the land and oceans, 51%. Others, we've got 6% reflected by the atmosphere, so it doesn't even make it to the earth. It's reflected by our atmosphere. 20% is absorbed or reflected by clouds. 4% is reflected by Earth's surface. So remember, light or dark surfaces reflect light. Right. Light surfaces reflect light. So where on Earth do you think reflection of light is occurring? Right. The poles, right? The ice caps. That's where a lot of light is being reflected. Right? So we've got 4% of Earth surface is reflecting light. Now, we've got some transferring. So energy changes from solar radiation here to long wave radiation, right? Radiating heat away from Earth. As it warms, it radiates heat away from Earth. Okay, so we've got radiated directly back into space is roughly 6%. 64% radiated to space from. So all this is showing you is that we've got solar radiation coming in, and it goes to different places. And then we lose some radiation as well, right? It hits Earth, it warms Earth, but then as Earth warms, some of the radiation is lost to space or the atmosphere or clouds or whatnot, right? So that's one image. Okay, this image is another one showing you radiation. Right, so we've got these really short, high-energy solar waves entering our atmosphere, hitting our Earth. Right, some of the solar energy is reflected by Earth's surface back out into space. Solar energy from the sun passes through the atmosphere and heats Earth's surface. Right, energy is not reflected or absorbed by atmosphere's heat. Heats the surface, so it's not absorbed, it's not reflected. It's just heating that surface. Some solar energy is absorbed by the atmosphere. Some solar energy is reflected out to space by the clouds, aerosol gas, and atmosphere, so on and so forth. Right? So energy's coming in, some energy's leaving. Remember, this is an external source of energy. That's radiation. Okay? The second kind of heat transfer that happens on Earth is what's called conduction. Conduction, so the top few centimeters of the atmosphere, right down close to the ground, is very, very hot, especially on a very sunny day. If you've ever been out on a turf field, like a football field or a soccer field that's turf, and you lay down on the ground on a really sunny day, what do you notice? It's extremely hot. It's much hotter down here, close to the ground, than it is 6 feet higher. And that's because of a process called conduction. Conduction, the particles have to touch each other in order to warm each other. Okay, so the first few centimeters of Earth are warmed by the surface because they're close to the surface and the heat gets passed to them. So sunlight hits the surface, warms the surface. By warming the surface, the particles next to the surface get warmed, and then they transfer energy to the particles above them, and they transfer energy to the particles above them, and particles above them, and particles above them, and particles above them. And eventually, each time the energy is transferred, you lose a little bit of energy. So right, we get to about, maybe 18, 24 inches, and conduction really stops because too much energy has been lost from the particles banging into the next particles and banging into the next particles. Conduction really comes into play if you're holding a piece of metal, right? You're holding a piece of metal, and you put that piece of metal, maybe it's a metal spoon, for example. You put that piece of, that metal spoon or that knife or that whatever, piece of metal, and you hold it over a lamp. Not a lamp. A flame, a candle, whatever, right? Eventually, what's going to happen to the piece that you're holding on to? It's going to heat up, right? It's going to get really, really hot. But it's not traveling over the flame. It's not the other end's on the flame. So how is the heat getting all the way down here? Well, right, this flame heats up the particles that the flame is touching. Those particles then bang into their neighbors and heat them up. And then they bang in, bang, 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 all the way up to where your fingers are holding, and you say, wow, that's hot. That's getting really, really hot, right? That's conduction. Particles have to be touching in order for conduction to occur, okay? Because it's a solid surface, right? And the particles heat up here, and then they bang into their neighbors. And by banging into them, they heat up and bang and bang, 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 right? They heat up and heat up and heat up and heat up. That's conduction, okay? Then the very last heat transfer, the way that heat Earth's surface is heated is by convection, okay? As the air close to the surface is heated because of conduction, right? That air then rises. We know hot air rises because the particles are further spread out, so they're less dense. Less dense items go up to the top. That's why ice floats in water, because ice is less dense than water, so it floats. Well, warm air is less dense than cold air, so the warm air that's being heated right by the surface travels upward. What replaces that warm air? Cold air starts to replace that warm air, and as that cold air starts to replace it, what happens to it? It gets warm and it starts to rise, and so it's called convection currents. Same thing happens in the core or the mantle of Earth, right? That gravitational contraction, going all the way back to the beginning of these notes. Gravitational contraction. Particles are being compressed towards the center. As they get towards the center, they heat up. So they heat up and they want to go towards the surface. So it starts this current within the magma, within the mantle. Same thing happens in our air, in our atmosphere, right? Warm air towards the surface starts to rise. Cold air replaces it. As the warm air rises, what happens to it? It starts to cool off, and then it starts to sink again. Gets warmed up, goes up, cools down. Warms up, cools off, goes down. And we see these currents all around our planet. These convection currents really help cause wind patterns and climate change, climate patterns, and so on. So, this rising and cooling of air or water, same thing happens with the oceans, right? We have convection currents in the oceans where the surface is warming water, and currents take that warm water down to the bottom, and as it cools off, so we've got these different things going on. This is another example, right? This just is an illustration of a pot of water, right? You put a pot of water on here. Here's the heat source. So the water directly in the bottom of the pan is getting heated. As it gets heated, where does it go? Hot water rises. And as it rises, it cools off. And so as it cools off, it sinks back down to the bottom. And it gets hot again, and it rises. And so we have these currents, where these cyclical patterns where we've got hot magma or hot water or hot air rising. As it rises, it cools off and sinks, right? So 3 ways that energy is heating the earth, right? Radiation, which is how the sun gets its energy to us. That's the only way the sun gets energy to us, is through solar radiation, right? That's the only type of energy that can travel through space. And then we have conduction, where particles have to be touching, right? So the surface, the air very close to the surface, because the surface is absorbing that sunlight, so the surface is warming. The particles next to the surface get warm and bang into the particles above them, above them, above them. Eventually, right, we warm the surface of the earth, and then that hot air rises, cold air replaces it, and we cause this convection current to occur. That's it. That does it. Okay. Don't forget to write down some questions that you had throughout the notes, and we'll talk about this tomorrow. Peace out, homies!